Welcome to the 13th lecture on circles. In the last lecture, we had discussed the method of deriving the equation of family of circles. So, one special class of family of circles is those family of circles which touch a fixed point. So, let us say that we have a fixed point whose coordinates are x1, y1, and let us say that there is this line, straight line, whose equation is y minus y1 equal to m times x minus x1. So, this point x1 y1 lies on this straight line. So, we are going to find the equation of the family of circles which touch this straight line at exactly this point only. So, obviously, there are infinitely many circles. For example, this could be one circle, this could be another circle, or this could be another one. So, what is the general equation of all these type of circles? So, that is the question that we are trying to address here. So, for any such circle which touches, so let us say this particular circle which touches this straight line at x1 y1. So, let us say that the general equation of such a circle is and the center is minus g minus f. So, obviously, if we join the center and this point x1 y1, then this angle is 90 degrees, because since this circle touches this straight line at x1 y1, the straight line is actually a tangent to the circle at this point. So, therefore, the slope of the product of the slope of this straight line, which is the perpendicular to the tangent from the center, and the slope m of the straight line itself. So, the product of slope m and the slope of this perpendicular should be minus 1. So, that is how we are going to start. The slope of this perpendicular is clearly y1 minus f, which is y1 plus f divided by x1 minus g, which is x1 plus g, times the slope of the straight line, which is m, should be minus 1. And therefore, from here what we end up getting is that m times y1 plus f plus x1 plus g equals 0. So, now what we can do is we can use this information over here to derive the equation of the family of all such circles. So, from here what we see is that we can derive an equation for G. So, what we see is that G is equal to minus x1 minus m times y1 plus f. So, what we will do now is we will take this expression for G and we will substitute it over here, and let us see what we get then. So, when we do that, what we get is x square plus y square plus 2 times x times g. So, instead of g we use the derived expression, which is this, plus 2 times f times y plus c equals 0. But we also know that the radius of since the center is minus g minus f, the radius or the squared radius of this circle is, from this equation the squared radius is g square plus f square minus c, and just by looking at this figure, the squared radius is the squared Euclidean distance between this point and the center, which is x 1 plus g whole square plus y 1 plus f whole square. So, therefore, this and this should obviously be equal. So, from here we see that c must be equal to g square plus f square minus x 1 plus g whole square minus y 1 plus f whole square. So, this is another expression that we get for c in terms of the coordinates of the center of the circle and of course, the fixed point x 1 y 1. So, we will use this right hand side over here, then what we get is x square plus y square plus 2x into minus x 1 minus m y 1 plus f into 2y minus 2mx plus c equal to 0, but instead of c we are going to use the expression which we derived just now, which is g square plus f square minus this is a minus equals 0. Of course, there is going to be some cancellation over here. So, on further simplification we get and then what we also do is we substitute g equal to minus x 1 minus m times y 1 plus f over here, and when we do that we get so this is the final equation for the family of circles, which of course depends on, so this is the free parameter f. So, we change f, we get the equation of different circles, but the common property of all these circles is that they touch that straight line y minus y 1 equals m times x minus x 1 at the point x 1 y 1. This can again be further simplified, and so we just take this part which depends on f. So, there are some special cases for this situation where we are interested in finding the equation of family of circles touching that straight line. The two special cases are, one is when the straight line is parallel to the x axis, the other is one when the straight line is parallel to the y axis. So, we will take these two special cases now. So, suppose this is the straight line which is parallel to the y axis. Here is the point x1, y1, and we are looking for all such circles which touch this point x1, y1. So, which touch this straight line at this point x1, y1. Clearly, the center of all such circles should have a y coordinate which is equal to y1. Let us say the x coordinate is minus g. In that case, the equation of all such circles is x plus g whole square plus y minus y1 whole square is equal to the square radius, and the square radius is simply x1 plus g whole square. Again, if we simplify this, what we get is x square plus 2gx plus g square plus y minus y1 whole square is x1 square plus g square plus 2gx1. So, g square gets cancelled, and then what we get is x square plus y minus y1 whole square plus 2g into x minus x1 minus x1 square is 0. So, this is going to be the equation of all those circles which touch this line parallel to the y axis at the point x1, y1. We can even simplify this further, and we can write it as, so this x square can be written as x minus x1 whole square plus 2x x1 minus x1 square. So, this is x square plus the remaining part of the equation which can be further simplified to x minus x1 square plus y minus y1 whole square plus 2g into x minus x1 plus 2x x1 minus 2x1 square equals 0, which is plus x minus x1 into 2g plus 2x1 equals 0. So, we can think of this as the free parameter k, and therefore, the family of all such circles which touch a straight line parallel to the y axis at a given point x1 y1 is given by this equation. So, if we change this parameter k, we get different and different circles, and it is not very difficult to see that if we put x equal to x1 and y equal to y1, this left hand side indeed evaluates to 0, which shows that the point x1 y1 indeed lies on this circle, on all such circles irrespective of the value of k. The second case is when the straight line happens to be parallel to the x axis for any circle which touches this straight line at a point x1 y1. The x coordinate of the center of the circle will obviously be x1. Let us say the y coordinate is minus f, and then in a similar manner we can write that the equation of this circle will be x minus x1 whole square plus y minus f, which is y plus f whole square is equal to the squared radius. The squared radius is obviously the distance between this point and this point, the squared distance between this point and this point, which is equal to simply y1 plus f whole square. Again, if we simplify this, we are going to get the equation of the family of circles to be of this type, where k is some which is the free parameter. So, even if we go back to the general equation of a family of circles which touches the straight line y minus y1 equal to m times x minus x1 at the point x1 y1. So, this is what we had derived. So, this can be further simplified, and I leave that as an exercise. So, this entire equation can be rewritten as x minus x1 whole square plus y minus y1 whole square plus k into y minus y1 minus m times x minus x1 equals 0. And it is not very difficult. I think what we just need to do is we need to replace this x square and y square by introducing these two terms. So, we can write this x square as x minus x1 whole square plus 2x x1 minus x1 square, and we can write y square as y minus y1 whole square plus 2y y1 minus y1 square, and then we can write the remaining terms as it is. So, this term here is minus 2x x1, the next term is minus 2 mx y1. So, this and this will get cancelled. Then here we have plus 2 fy minus 2 m f x minus x1 square minus y1 square plus here we get 2 x1 square plus 2m x1 into y1 plus f minus 2 f y1 equals 0. So, what we see is that this minus x1 square and the minus x1 square here, they become minus 2 x1 square, which gets cancelled with the plus 2 x1 square here, and then the remaining terms can be simplified further. We get plus this minus y1 square and this can be combined and written as minus 2 y1 square, and then this entire thing can be written as 2 y1 into y minus y1. Further, the term 2 mx1 y1 and minus 2 mx y1 can be combined, and we get plus 2 y1 into m minus x minus x1. So, we have combined this and this term, and then we can also combine this and this term. We get plus 2f into y minus y1, and then what remains is just this term with this term here, which is going to give us plus 2mf minus 2mf into x minus x1 equals 0. So, if we again simplify this further, we get plus 2 y1 into y minus y1 minus m times x minus x1, which is combining this and this term, and then plus 2f into y minus y1 minus m into x minus x1 equals 0. And then of course, this and this is same, so we can write plus 2 times y1 plus f into equals 0, and this is actually the parameter k. So, finally, we do get this form for the family of circles, and it is clear that irrespective of the value of k, if we put x equal to x1 and y equal to y1 here, the left hand side evaluates to 0, which shows that the point x1 y1 lies on this circle, on all these circles, whatever may be the value of k. So, that finishes our discussion on the equations of family of circles. Next, we are going to take up the how to derive the equation of a chord if we are given the midpoint of a chord. So, suppose that let us say that we have a circle here, having center at minus g minus f. Let us say there is a chord, and let us say that we know that the midpoint of this chord is given to us, and it is x1 y1, and then we are asked to find the equation of the chord. So, clearly we know that if we join the midpoint of the chord to the center of the circle, then this angle is 90 degrees. Let us say there is any other point x y on the chord, then the slope of this chord is and the slope of this straight line is equal to y1 minus minus f divided by x1 minus minus g, which is this. But since these two straight lines are at 90 degrees, the product of this slope should be minus 1. And therefore, this times this should be minus 1. Which can be simplified to and this is the equation of the chord. So, next we are interested in finding the equation of the chord. So, let us say that. So, next let us say that we are given a point P having coordinates x1 y1 and a circle whose equation is also given to us. Let us say that this point P is outside this circle. So, clearly there are two tangents PT1 and PT2 from the point P to the given circle, and if we join T1 T2, it is nothing but a chord. So, the objective now is to find the equation of this chord of contact. So, this is called the chord of contact. So, this equation of the chord of contact T1 T2 for a given point P outside a given circle having this equation. So, of course, we know the radius of this circle r, which is given by square root of g square plus f square minus c. The length of these tangents can also be found out, because we know that this is 90 degrees, and if we join P with the center O, then PT1O is a right angle triangle, Therefore, from the Pythagoras theorem we know that the squared distance PO is equal to L square plus R square. Further, PO square is, since we know these two coordinates, PO square is and therefore, if we substitute this expression over here, we get L is equal to square root of PO square minus R square. So, we know L also. Now, consider the circle. Let us consider the circle whose center is at P and having radius equal to L. So, this circle shown in red has center P, radius L. Clearly, this circle or it passes through T1 and T2, and therefore, it is clear that T1 and T2 are the point of intersection between this red circle and the given circle whose equation is this. And therefore, the equation of this chord T1 T2 which we want to find out is nothing but the equation of the radical axis between the red circle and the given black circle, and this we know earlier. So, the equation of this red circle is x minus x1 whole square plus y minus y1 whole square is L square, and that of the given circle is this equation. So, let us say this is S1, this is S2. So, when we write it, we have to write it like this, and the equation of the radical axis will be simply S1 minus S2 equal to 0. And therefore, the equation for the chord of contact is given by, we just need to subtract S1 S2 from S1 and we get on further simplification, we get that is So, this is the equation of the chord of contact. So, next we will also for the same situation so we know how to find L and R. So, let us say we are asked to find the length of this chord of contact. So, it is not very difficult because we see that this angle will be 90 degrees. Let us say if this angle is theta, then this angle is 90 minus theta, but because this entire angle is 90, this angle is also theta. Further, this point, which is the intersection of the chord of contact with the straight line joining the center O to the point P, this point is the midpoint of this chord, and therefore, if this length is x, then this is also x. So, let this midpoint be M, and let us say that this small length here OM, we will denote it as by H. So, we have this triangle T1MO, T1MO like this, and we also have the triangle PT1O. One can see that all the three angles of these two triangles are same, and therefore, triangle T1MO is similar to triangle T1PO, and therefore, the ratios of the corresponding sides must be the same. Hence, x by L is equal to h by r is equal to r by square root of r square plus L square, because of similarity. And from here we get x equal to R L divided by r square plus square root of r square plus L square, and h equal to r square by square root of r square plus L square, and h equal to r square by square root of r square plus L square. And therefore, the length of the chord of contact T1, T2 is simply twice that of x. So, which is 2 times x, which is 2 R L by square root of r square plus L square. So, we can find many other interesting things about this given this situation. For example, we can find out the area of the triangle PT1T2. So, PT1T2. So, how do we do that? Now, clearly the total area of the quadrilateral PT1OT2 is the sum of the areas of these two. So, this triangle area plus area of this triangle will come out to be L into R, because the area of PT1O is half into L into R, and the area of PT2O is the same. Further, the area of OT1T2 is simply H into X. We can use the previously derived values of H and X, and we get this to be R cube L by R square plus L square. And therefore, area of P T1 T2 is equal to area of P T1 O T2 minus area of O T1 T2, which is equal to which equals this expression. So, we can also find out this angle subtended by the two tangents from this point P. So, clearly this angle is simply tan inverse of R by L and therefore, this entire angle is angle T1P, T2 is two times tan inverse of R by L, which is simply so we can use the tan inverse A plus tan inverse B formula and this is what we get. Finally, another type of question that can be asked is, for the same setup, we could be asked to find the equation of the circle which circumscribes the triangle PT1 T2. So, we have to find the equation of this circle in red which passes through P, T1 and T2. So, this circle passes through T1 and T2, and we know that T1 and T2 are the point of intersection of the given circle in black and this circle in blue. So, this circle is in blue has its center at P and a radius equal to L. So, clearly this circle in blue passes through T1 and T2 and it intersects the given circle in black at T1 and T2. So, therefore, if we consider the family of all circles which pass through the points T1 and T2, which are point of intersection of the blue and the black circle, then this red circle should belong to that family of circles. So, that is how we will try to find out the equation of this red circle. So, the equation of this given circle is S1 and that of this red circle is simply which can be simplified to so these two circles are known to us. The equation of family of all circles which pass through the point of intersection of these two circles is where lambda is a free parameter. So, if we change lambda by changing lambda we will get different circles which pass through T1 and T2. This is the point of intersection of these two circles. So, this equation is now one such circle is this red circle, but we know that the red circle also passes through x1 y1. Therefore, if we put x equal to x1 and y equal to y1, then this left hand side should evaluate to 0. So, when we do that, we get which implies that lambda must be equal to by L square. So, therefore, we have found out the value of lambda, and then what we need to simply do is need to, because x1 y1 g f and c are known to us, they are given to us, L is also given known to us. In fact, L square is, we use this formula, and r square is the square of this. If we use that here, what we will see is that this numerator is L square, and therefore, lambda equal to 1. Hence, the equation of this red circle is nothing but we just need to put lambda equal to 1 in this equation, and therefore, this is the equation of the red circle. Thank you.